Welcome to day one. One thing I forgot to mention in the intro is I sometimes get excited and start speaking quickly. One of the benefits of these being in YouTube is if I'm speaking quickly, you can slow me down. If I'm speaking too slowly, which is unusual, you can speed me up. And you can also pause the video and you can rewatch it. So there are some positives to having this on video. The one thing that's I'm not thrilled about is the way you see these things at the bottom of the screen here, the stop screen mirroring. If I've tried other views, this is actually how I demonstrate. I actually show it in my class when I'm teaching a live class, because unfortunately, if I hit document, it goes tall. And if you're trying to read this on a small device, it's very challenging. So we're going to stick with just the basic screen mirroring. Please just I apologize for the stop and stuff at the bottom. So let's get going. The goal for today is really a basic introduction and some basic terminology and in statistics. So we want to talk about what is statistics and what do we do with statistics. Now, quick thing, my mom does not get the flu shot every year. She's 76, 77. But she remembers back in 1960 something that she got the flu shot and then she got the flu and she was very ill. Now, for her, she's made the decision that she doesn't want to get the flu shot. I will show her the information, but she's like, nope, I get the flu shot, I get sick. This is anecdotal evidence that my mother, when she gets the flu shot, gets sick. Does that mean every time she gets it or anybody else gets the flu shot, they get sick? No. But this is what we want to move away from, the thinking of we hear something and say, oh, well, it happened to someone we know, it must be true. Or maybe it's by saying, oh, we know someone that's happened to, think it's more prevalent than it actually is. So statistics is the science of decision making using statistical investigations. So we actually look at data. We don't just say, oh, well, I heard from someone. So we want to make good decisions being informed based on data, not just based on hearsay. It's a science and in some degree an art of collecting the best possible data and analyzing and interpreting the data to make the best decisions possible and to give people the best information possible. You do not have to memorize these. Remember, when you're taking an exam or a quiz, you will have your notes in front of you. But that being said, they will be, I'm not say time pressure, like, oh my gosh, you have to go as fast as humanly possible. But you're going to want to be familiar with and study for the exams, not as if they were closed book, but that you know your information well enough. And we'll talk about that, of course, as the exams get closer. But first of all, the 6 steps of statistical investigations. You always want to start with a research hypothesis. That's what we're always going back to, is we have to ask a research question. We want to know something about something. If we didn't have a research question, if we already knew the answer, we wouldn't be asking a question like, how tall am I? Well, is that a research question? Some would argue, well, yes, it is. In statistical research questions, we're talking about something that we that we can't find the answer easily. I can stand up, have someone measure me, I'm 5'7". On the other hand, what's the average height of females at Cal Poly? I would not know right off the top of my head. So you design, this is a 6-step process. We design and a study and collect data. We explore the data, look at it, see if there are outliers. Don't worry, these things, we're going to look at variables. There's a lot of things we're going to look at, but we're going to take it one step at a time. So don't worry, this is just a brief overview. Now, the important thing is when we explore data, we then look at it and we draw inferences. It means we come up with some estimations. We come up with to see if it tells us anything. So we look at significance estimation and logic of inference. And once again, we'll talk more about these down the road. We formulate conclusions, which we want to take the information we have, come to some conclusions, see if we can generalize it, maybe we can't. There's a lot of factors here. But once again, this is just a brief overview. And you're like, well, but then I've answered the question. Well, we're going to look back and see what we did, and we're going to look ahead. Generally speaking, when you get done with the research question, it leads to more questions, or you realize that the study could have been done better to change what we did. So For example, we want to start with looking at these to figure out whether or not something is a research question. So which of the following questions are statistical in nature and so are research questions? I suggest pausing the video for a second and see if you can answer these yes or no. Okay, I'm assuming you paused and you're back. Have you ever gone skiing? Is that just a yes or no question? Yeah, I just ask you that, you tell me. So no, that is not, not statistical in nature. So the first one is no. Do I need a good study? Absolutely not. Number two, what percentage of US adults went skiing? Well, we can't just answer that. I have no idea what the percentage is. I'm a Vermonter and a lot of people ski, but I don't know. So would you say that that is a research question? In statistical, in nature? Yes. On average, how tall are sequoia trees? Well, I don't know right off the top of my head. Let's say we didn't have the information. Would a statistical study need to be done to actually come up with that? Yes. How many players are the start in a basketball team with the tip off? That's a rule. It doesn't change, so that is not a research question. As we go through the quarter, we're going to focus on research questions, then they're going to get more and more complicated. Let's see, basic terminology. This is where we're going to come back to this again and again and again. And so even by exam 2, 3, 4, you're going to still be asked to be able to identify these things. So don't just think statistics is kind of like math in the sense of you learn to add, subtract. And then once you get up to, let's say you're taking pre-calculus and you're working with functions, do you still need to remember how to add and subtract? Absolutely. So this is where the basic terminology, if you get it now, it's going to make the rest of the quarter easier. So that's why we're going to spend some time on it and make sure you do the homework, hand it in, and get these concepts down. So the first one is an observational unit. It's any entity on which data can be gathered. So for instance, could a person be a observational unit? Absolutely. You could look at hair color. What's the hair color? What is the eye color? How tall is a person? So you could gather information about an individual. Could you do it about dogs? Definitely. Trees, sure. So the thing is to look at the research question, go back to that and see what the observational unit is in the research question. A sample. So a sample is a set of the observational units on which we actually collect data. So for instance, if we're interested how tall the average female is at Cal Poly, we would not actually go and measure every single female. We would take a sample, we'd take a set, measure them, and hopefully be representative. In other words, it would reflect what the actual percentage is, or what the actual height is. Population. That's all possible observational units about whom we want to make any inference or conclusion. So that, in the case I've been talking about, would be every single female who's at Cal Poly. Populations can be finite. So example, all Cal Poly students. Sometimes though, we can use a sample to infer about a process which is potentially infinite or never ending. For example, a coin. A fair coin, when you toss it, it's equally likely to be heads or tails. We all agree on this, I hope. A process could be 10 coin flips. What's the average number of heads, let's say? And we do that again and again and again and again. Or if you're producing things and let's say you're in a production and you want to see what percentage of defectives come out. Now that's something you can measure, and then you can hopefully make adjustments down the road. How would that relate to statistics? I'm just more throwing that out there to show a process that we could look at. Variables. Okay, let's see. The recorded characteristics. Now sometimes this is where students start to get a little bit confused about the observational units. So they can be quantitative in nature. In other words, they're measured or recorded as a numerical quantity. Categorical, on the other hand, is measured as a label or category. So, pretty easy so far. Quantitative, I think price, height. But what about like a barcode? Think about it, a barcode. Can you take an average number for a barcode, like average out the numbers of the barcodes and that means something? No, that would actually be categorical. So pause the video, do for this quick check, identify which of these below is quantitative or categorical. Okay, so weight, quantitative, easy, quick and easy. We can average them, right? Take the average, of weights from our observational units, or our people in this case. A phone number, categorical. You can't average phone numbers, that wouldn't make any sense. How about prices? Prices, yes, they're quantitative, they're numerical quantity, and you can take the average of them. How about whether or not over the age of 50? You're like, well, it's ages, but the question is whether or not. So this is something I want to just talk about for a moment. Over the age of 50, what is the potential answers there? Am I over the age of 50? Either yes or no. Okay, if it's a yes or no, it's going to be categorical, but it's also going to be binary. All right, binary meaning there's only two choices, yes or no. So for instance, what color is your hair? Well, that would be categorical in nature because your hair is whatever color it is. Is your hair purple? Now that's entirely different. Still asking about hair color, but is your hair purple? Do you answer yes or no? Correct. You answer yes or no. So it's categorical and it's binary. Take a moment, pause please, and try these examples that are below. Okay, for each of the following research questions, so number one is research question. We already told the research questions, so you know that they are. Identify the OU, observational unit, the variables, and what type of variable they are. That's not written there, but on an exam it would be. Population, and describe what a sample should comprise. So for number one, what % of US adults went skiing in 2019? The observational unit, well, let's see. Are they US adults is what we're interested in? Yes. We want to look at, in theory, each US adult, and to make it even more specific, in 2019. So that's who we're interested in. I'm going to skip variable for just a moment and go to population. The population is all US adults in 2019. So the observational unit, we're looking at an individual. A population are all that we can possibly choose from. Now in this case, the variable, what % of US adults went skiing? So what are we looking for in that case? I would say whether or not you went skiing in 2019. That's going to be categorical in nature. Is it binary? Is it yes or no? Yes, so it's also binary. And a sample. Now, we didn't talk specifically about a sample size, but let's just say, I'm going to say it's an arbitrary number. Let's say we're going to choose 1,000 US adults in 2019. All right, or people who were adults in 2019. Once again, if you didn't pause, please take a second and a moment and pause and see if you can answer this. I'm going to pause this for a moment and then I'm going to write out the answers, and I want you to check your answers versus mine. Okay, hopefully You've got the same answers I did. You'll notice under variable, it says in meters or feet. In general, in a research question, it would specify whether it was in meters or feet. In this case, it was not. Height of each tree would be fine for the answer. It is quantitative since we're looking at height. Remember, we always want to go back and look at the research question when you're answering these questions. So that's where you always want to go back to look, just as a reminder. Okay, if you need to pause this again to make any adjustments, please do to your answers. Now, which of the following are the legitimate variables from sequoia tree to sequoia tree? If it is a legitimate variable, is it categorical or quantitative? I'm also going to say, if it is categorical, is it binary? Remember, quantitative can never be not binary, because binary means there's yes or no. There's only two options. So once again, please pause the video and do your best to see what you can get out of these. Get these done. All right, welcome back. Hopefully you did these and found it easy. First of all, height in meters. Well, we've already just talked about that. We know that's quantitative. The shortest tree. Nope, it is not a variable. There's one answer, okay? You'll find the shortest tree. There is one answer. It's not a variable that we would do a study on or research study with. Average height of trees in meters. That is actually an answer. That's what you're going to get out of the study. The trees that are in the giant forest, well, no, that's just a statement. No, that's just a statement. Whether a tree is in the giant forest grove. Ah, good one. Is it or is it not? So it's categorical. Is it binary? It's yes or no. So I'm going to say, yep, it's also binary in nature. What is the percent of trees that are taller than 60 meters? Nope. Once again, it's not a variable. There's one answer that we'd get. Is the girth at ground related to the height of the tree? Not a variable. That is actually a research question. Something you would look at. There are variables in there, the girth at the ground and the height, but there's an answer. Remember, variables are going to vary from tree to tree. So that's what we're looking at as we do these. Coming down to some more vocabulary. Statistic. A statistic is known. We find those, all right? So we take our sample, we do some calculation. A statistic is a number calculated from observed data. A statistic, I'm having a hard time with that one now. A statistic describes some characteristic of the sample. You're going to see statistic and not sample. Those are related. If you have a sample and you have numbers related to the sample, they're a statistic once you do whatever the calculation is you're asked to. The parameter, that's an unknown. And we won't know an exact parameter variable. It is a long run. Also, it's called the true value, numerical property of a process or population. Parameters are usually unknown values because they're usually processes or populations. They're too large to collect complete data on. So it's something we would like to know about. You're going to notice that talks about the population, goes with the parameter, all right, or the process. So parameters are unknown. We usually say to the population. The statistic is unknown because we take some samples and we do some calculations to come up to a statistic. In the context of this skiing example, identify the statistic. Well, the statistic is what we want to know. We want to know the percent of excuse me, let me erase there mentally, go back a little bit. In the context of the ski example, restart, reboot there, sorry. Identify the statistic and the parameter. The parameter is what we really want to know, but we don't know. It's the percent of all US adults in the population who went skiing in 2019. The statistic, on the other hand, is the percent of US adults in the sample who went skiing in 2019. So once again, you see population with parameter and sample with statistic. In the context of I want you to try this on your own, so pause for a moment. But in the context of Cal Poly students, identify which one is the statistic and which is the parameter. Hopefully, what you came up with is statistic and parameter. Survey of 100 students. There are a lot more than 100 students at Cal Poly, as you're probably well aware already. So that was a calculated, who they asked had back problems, and the proportion of Cal Poly students who went skiing. You notice it doesn't say all. You can kind of imagine that it's there. It's not always going to say all, but when it talks in general, you know they're talking about the parameter. So let's look at some basic charts and basic graphs and statistics. I took a moment and paused, and you should pause for a moment too. I wrote down something about probability. Just as a reminder, probabilities are the likelihood that something's going to happen. It's the numbers between 0 and 1. It can, or between 0 and 100%. So the chance of rain is 0% today. Well, there's no chance that it can rain. Or it's 100%. Literally, it is raining at this very moment. And it can be anywhere between 0 and 100. It can't be negative. So you can't have a negative probability. It either is 0, which would be not, or 1, which would be absolutely certain. And it can't be over 100%. It absolutely cannot be over 100%. I know in Star Trek and those things, they talk about going to 110% of the reactor or whatever. What they're meaning is over what they would call the safe value or the regular operating, but that's not at all what we're talking about here. Everything should be between 0 and 1 or between 0 and 100%. So I just wanted to remind everyone of that before we moved on. So for basic graphs and statistics, for categorical data, a simple and effective way to record the data distribution is a bar graph. Bar graphs are nice. They're easy to read. You need to be a little bit careful with them to make sure that they actually show things so that you can actually see what's going on. Like in this one that you see, do you have back problems? Putting 1% without the number above it would be meaningless. Like if you just did it, this one I actually have it labeled, but if you didn't have it labeled, you could see it's a little over 30 for the yes and a little over, close to 70 for no. So those are reasonable. A simple statistic that's used with categorical is for sample proportion is the number of successes, and it's denoted by p hat. So the little accent above there is called the hat, p hat. A simple statistic, yeah, I just said that. Sorry about that. Example, based on the back problems proportion above that we talked about in one of the examples, we could display the information this way. You're going to notice you absolutely have to label the axes. So label axes, just like in math, we need to do that. In this case, the question was, I believe if we go back up, In a survey of 100 students, so this is here, 32% reported back problems. So this is looking at that. What that said is p hat came from that survey is 32%, which is the same thing as 0.32. You know, it's between 0 and 1. And that's the proportion of Cal Poly students in the sample who said they have back problems. Notice that we start at 0 and we go positive, just as in normal graphs, but make sure you label your axes. For quantitative data, on the other hand, a simple way to describe it is with a dot plot. So in this example, below are dot plots displaying the distribution of the heights of players on a women's field hockey team and the heights of players on a women's basketball team. So once again, these axes should be labeled. I apologize. It did not show, when I printed this one, I was not able to make it be labeled. But this would be the like a count for each of these. So what are these? What are these various dots? So n equals 25. N is the sample size. If you looked and you counted, you would see that there are exactly 25 dots. So the dot here is the height of a player. So it was measured. So this could be the occurrence or the count, or a count, somehow measured, that tells us what we got there. So looking at this, we have field hockey and we have basketball. Notice though, this one goes between 62 for field hockey and 70, and these are in inches. The basketball team goes from 65 to 80. Now, looking at these without doing any calculations, knowing that each dot is a player, what team appears to be taller on average? Well, by looking at it, it's pretty obvious it's the basketball players. If you look at roughly where the center is, I'd say it's right about here. The center for the field hockey players is down around in here probably. And we could figure that out exactly, but we don't need to. We're just looking at the plots to see what we can determine. Which team appears to have more variability, in other words, less consistency in heights? So we're talking about spread of the data here, okay? Some are tall, some are short, right? On each of these, some are taller, some are shorter, excuse me. But what has the bigger spread? Well, if I look at it, you have between field hockey players are between 62 and 70 inches, whereas basketball players are between 65 and 80 inches. Which would you say has the bigger spread? Hopefully, once again, you say basketball. There are two simple numerical statistics that we use very often, the mean or average, and that just tells you what a typical value in the data set is. So where the middle is, and that's what that's going to give us. Typical value, where the middle is. The standard deviation, frequently referred to as just SD, when you see it written to save ourselves a lot of writing, is a measure of typically how far away the observations in the data set are from the mean. So this is looking at how much variability there is. A data set with observations that are far away from the mean will have a larger standard deviation than a data set with observations which are close to the mean. So which team should have the higher mean height? Well, we looked at it and we looked at roughly where the center was, center being the typical value, the average value. And we already said that that was basketball. Which team should have the greater standard deviation? Once again, basketball, because they had more variation in the heights. Now imagine that an athlete from one of the two teams told you she needs to go to practice. You estimate that she's 65 inches tall. If you had to guess, which team do you think she's from, and how did you decide? Alrighty, I'm gonna say, go look at the two spreads, okay? And see if that'll help you come up with your answer. Pause it for a second and see if you can get the answer. Alrighty. Hopefully you came up with field hockey. Looking at the dot plots, we see that there is only one, I believe, a basketball player versus a lot more that field hockey players. So if she's 65 inches, the odds are better that she will be on the field hockey team. Thanks. Have a great day. And this made it through your first class.